Good morning, everybody. I'm glad some people came back. That's great. I was afraid it would just be three of us here this morning. That's awesome. So this is Shrivas. Some of you heard him say a few things yesterday. So Shrivas came. Shrivas is a long-time colleague and friend of mine. Shrivas came to work with us in Cambridge in 2010 as a postdoc. I can remember very well interviewing him. And
had a lot more hair than
me or you?
I did.
And so okay. Did you. Yeah, I definitely had more hair. Yeah, and it was very clear at the time that he was exceedingly smart and funny and fun to be around. I left Cambridge actually a couple of years later. Shrivas stayed there. He still has a joint appointment at Cambridge, but has moved to an assistant professorship at the University of Kent. And he now lives...
Where Adrian's from, actually.
Yes. He now lives in a town called Rochester, which is just a few miles from the town that I was born. So it's quite exciting to have Shrivas back, knowing that every day he gets to wake up close to Gravesend in Kent. So Shrivas is going to talk about... What are you going to talk about? He's going to talk about EEG connectivity correlates of conscious states and contents, applications in disorders of consciousness. Welcome, Shrivas.
Thank you. Thanks, Andrew, for the introduction. So I've got a talk that sort of covers a whole bunch of different things. Some of you probably heard some bits of it at some point or the other. If you have heard it, so my apologies in advance. And in my talk, at least compared to yesterday, where we've talked a lot about methods, consciousness is front and center. Some of the methods, I'm sure, will be a matter of hot debate and perhaps even controversial if I'm lucky, so that we can then get the discussion going as to how we should be improving them. And that is exactly why I'm here. And when I was invited to come to the MNI, so I told my wife, said, oh, you know what, I'm going to the MNI. So what's that? What's the MNI? So clearly, she's not a neuroscientist. That's okay. Everybody can be one. But I said, I'm going to the MNI, and this is where Wilder Penfield did his studies. It's controversial, but today, a landmark and all that. She said, who's Wilder Penfield? So I said, okay, this is ridiculous. So I took a picture of this. I'm going to take it back home, not because of that, but because even the bins say Neuro on them. So it's, that's how Neuro we are right now. So it's amazing. So that's a great picture. I just took it yesterday. This is not doctored. Sorry? It's just so they don't get stolen. That's right. No, it's brilliant. So nobody would want to steal that. So absolutely. Anyway, so I'm very excited to be here and very excited to have a discussion with all of you on the real stuff, not to just present this, but also to have a discussion about where it goes from here. But here's the overall picture. Oh, it looks somewhat different on that screen, but you can still see it. Overall landscape. Now, this is a diagram that certainly in the DOC field is quite worn because I've used it a lot, but it's a simplistic representation of some of the ideas you've already heard yesterday. I won't repeat them all, but broadly speaking, captures the notion that consciousness is sort of, Stephen Laurie has popularized this notion of consciousness as having at least two dimensions, if not most likely more than that. A dimension along which you can measure consciousness as being wakeful, and a measure along which consciousness can be seen as being aware of your surroundings and your thoughts and so on. Most of us go through a cycle along both dimensions. Your levels of consciousness change all the time. Through the day, you basically go up and down. Your contents of consciousness change at an even faster rate. From moment to moment, you're aware of different things, of different sensory experiences. But it's a small part of the large set of processes that are going on in the brain. This is hardly surprising to us as neuroscientists. So there are a lot of different ways in which researchers have started to understand this landscape. And even two dimensions are enough to keep a lot of scientists busy for their entire careers. So they've looked at conscious wakefulness, just what does the brain look like when it's conscious? What does the brain look like when it's falling asleep, in deep sleep, so on. What I'm going to do is give you a bit of a tidbit of information about what light sleep looks like, because that's often a bit understudied, the process of just falling asleep. I'm going to look at general anesthesia, just give you a tidbit again, because I know speakers after me will go much deeper into it. And I will compare two states of consciousness wakefulness in terms of their different contents and show you what we can do with EEG. And of course, touch upon the vegetative state itself, which of course we've already heard a lot about yesterday. So let's start with just being wakeful. Now, the idea that really captured a lot of the imagination in this field, if you are into this stuff and if you go to ASSE, for example, the conference that's very popular in this context, the theory that Giulio Tononi at Wisconsin-Madison has developed really has got a lot of people talking, not because it's a solution to the problem, but it's a way to start thinking about it quantitatively, so that we neuroscientists can get a handle on it. And if you don't know about the theory, which is called Integrated Information Theory, or IIT, it's a theory that suggests that consciousness is information at some level, right? And the way it's, to put it across very simply, if you think about this great philosopher, artist, and thinker, Ernst Mach, in 1959, he took the sketch, The View from the Left Eye. The idea that though we know that our consciousness is a product of a combination of senses, if you just take away one of your two eyes, it doesn't mean your consciousness is fractionated. It's always unitary, right? The experience of your consciousness, though it's made up of different biological constituents and neurological constituents, is experienced as a unitary whole. It can't be broken up. At least consciousness can't examine its parts, its own parts. And that's one key idea in the theory. But also that any individual experience is different from all other experience you've had. So Ernst Mach might have smelled a rose, might have had a cup of coffee. All those individual experiences are kind of different from every other one, right? And of course, there are infinitely many such experiences. So consciousness is both integrated and differentiated. So Tononi has made a whole career out of this idea, because he's not just said that and left it at that. He's developed a whole theory surrounding how one could measure, quantifiably measure, the extent to which there is a balance between integration and differentiation in consciousness. And if you're interested in any of the ideas behind this, I, of course, encourage you to read his work, of which there's a lot. And quite recently, neuroscientists have started taking an interest in this, because they can say, okay, here's something I can actually touch and feel and measure using data, data like, for example, neuroimaging data. And neuroscientists have taken those two ideas I mentioned and then framed it in, okay, what does integration mean? Well, if I can measure signals in the brain, and if those signals have certain properties about the way they behave across multiple measuring sites, in terms of being more integrated or more differentiated, then I've got some handle on the extent to which a particular brain state has those properties. So integration can be seen as a greater amount of relationship. How you measure that relationship is exactly the controversial point. Or you can have more differentiation, both in space and in time. So here, this is a more differentiated state, because moment to moment, the brain is going through a sequence of different states. This is a paper from Christoph Koch and Tononi, who worked quite closely together on these ideas. I think this was in Nature Neuroscience, where they said, or it was a manifesto, more or less, and an update on the work that's been done, showing that states with more consciousness, in a quantifiable sense, have more integration and more differentiation at the same time. That's the idea. And there's some nice tests above this. It's not really all just theory. So here's a nice simple test where people in Massimini's group in Italy, in Milan, have done this work, which I'm sure some of you have heard of, where they've basically taken TMS, very well-known, well-established technique, pulse the brain with TMS, but instead of having stimuli that they look at in terms of the influence of TMS on stimuli, which is typically how TMS is used, they've looked at the pulse itself, the response to the TMS pulse in the brain, basically a magnetic current that then percolates through the brain, and have shown that in conscious wakefulness, you have a reentrancy and a complexity in the signal. So that's signal across multiple EEG electrodes that are measuring the response of the pulse. They socially construct that. And what they've done is shown a couple of things. First of all, what you see here is the site of the TMS pulse. The plus sign indicates where the peak is at any given time after the pulse, and you can see the peak moves around and comes back to places near where the original signal was. There's complexity, there is reentrancy, there is a prolonged activation far beyond the original pulse that lasts only a few milliseconds. So that's interesting. At this simple level, the cortical dynamics that ensue as a result of the pulse are both complex and reentrant. That's good. But they also show that in addition to that kind of integrated activation that's generated by the pulse, there is differentiation in the wakeful brain, in the sense that if you pulse different bits, so if you pulse there versus there, so precentral kind of cortex or occipital cortex, the response in that area is very different. So BA6 responds very differently from BA19 when this particular brain is awake. So those brain areas, because of the way they're connected, because of the way the architecture of the white matter in that area is different, produces different set of responses as a result of that pulse. Okay, so that's a good starting point. It's just a starting point to understand, okay, can we quantify the level of consciousness or the state of consciousness that his brain is in? If you look at light sleep, or if you start looking at sleep in general, here's what they've found. So if you just look at slow wave sleep, or this would be slightly deeper than light sleep, but you would be calling this non-REM sleep. So it's basically the early stages of sleep. What they show is that that complex re-entrancy of the signal disappears. So if you pulse the same brain that was pulsed before, but now is sleeping, the peak of the activation hardly moves from where the TMS pulse was. And the complexity of the signal, the envelope, is much, much simpler in a sense. It just dies away very quickly. It just kind of, it's like plonking a big rock in the first case in a pool of water and producing a lot of reverberations. Here, it's like plonking a rock in a thick, viscous liquid. Nothing really happens. It just doesn't move much. It just stays there. So the pulse becomes less interesting in its response. And also, what's nice is they've shown that the same areas pulsed before, which produced very different responses, if you remember, produce very similar responses now, and that's striking. So these are two different brain areas in the same person who was awake and is now asleep. So it's not just due to the physical architecture, but clearly the functional consequences of falling asleep have changed the signal you can measure, which is good. And we do something similar to this, and as I've alluded, some of the techniques we use here obviously are using EEG, but in fact at the scalp level. I'll tell you why we use the scalp as we go along. But one of the things we do is look at, for example, phase-like relationships with, of course, the understanding that anything at the scalp comes with the problem of having to deal with volume conduction, will have its limitations, which is why one of the great things I think that could come out of this workshop is an establishment of the best set of, the kind of optimal set of tools for doing host reconstruction, these kinds of resting state data, and it would be quite, in a sense, ideal that it comes out of the MNI and relationships here. So what we do, however, at the starting point of this sort of analysis is to just look at resting state data where there is no task, the brain is active, doing whatever it's doing, and looking at the connectivity with essentially a measure that is trying to ameliorate the influence of volume conduction, but cannot remove it completely. And that's the phase lag index. And after thresholding the connectivity map, we do produce essentially patterns like this. What this is essentially simply a visual representation of the connectivity across a set of senses, in this case, 91 senses. All I'm plotting here are strength of those connections, and I'm thresholding them so that you can see the strongest ones, and I'm coloring them based on what graph theory says are the connections representing regions of senses that basically are talking or are related to each other in a phase sense across the brain. Because you've got lots of senses, you can produce a relatively more interesting map, in the same sense that you can then use this to look at whether there's any structure in that connectivity. And what it turns out is, in the waking brain, just like what I've shown you just now, there is a particular pattern of connections, or particular set of connections that seems to be stronger than others across multiple sets of healthy volunteers we've looked at. It's a fairly easy to reproduce phenomenon across multiple different groups of people. It's not that difficult. Essentially saying that when you're awake, in the alpha band, you have a pattern of connections that is predominantly parietal, hardly surprising. We know alpha is parietal, but it's got connections to frontal areas through just measuring across the senses. So I can't really say much about where this connectivity is coming from, obviously not, but it tells me that across the scalp, which is a crude measure of any sense of space, there is some topographical differentiation. At the level of this detail, what we can then do is ask how this is changing across states of consciousness, and then quantify that using, for example, things like graph theory. And I'll show you an example of that just as we go along. So here's the first starting point. So what we looked at was, how does this pattern of connectivity change in rest as people are falling asleep? So this is what I call light sleep, because what we're doing here is, as participants come into the lab, let's say after lunch, you've had a nice meal, we ask you to do a simple task, a fairly simple semantic discrimination task, and then ask people to say, well, if you want to fall asleep, that's perfectly fine. Go ahead and do that. So we're not going to prevent you. The people initially are awake, they're doing the task, excellent. About 5 to 7 minutes, this is a typical participant, 5 to 7 minutes later, they start getting drowsy. As you can see, the responses slow down. That's what you're seeing along the y-axis. And they start slowing down further and further. They start missing very simple stimuli. They start becoming slower and start becoming unable to make a response, whether this was a animal word or a non-animal word. Simple tasks like that. And eventually, they just completely drop out. They fall asleep, right? And you will sometimes hear them snoring. at which point we might, in some way, either ask them to continue making responses, or if you want to measure what's happening as they fall asleep, we let them fall asleep, right? And we're just looking at what's happening when they're responsive versus when they're not. And this is a picture that popped up yesterday, but it's a very simple demonstration of what we should know, we know should exist in the data, which is that as people fall asleep, they go from responsive to unresponsive, alpha power, and connectivity drops. No, again, that's just a validation, a sanity check, that connectivity as measured this way, which is primarily frontoparietal. So I'm showing you the strongest connections. It drops, but the key point is that it's not just everything dropping, it's that in lower frequencies, you see an increase in connectivity at certain frequencies, especially in the theta band. Again, that's not new. We've known that theta power increases during the process of falling asleep. But what we also did was we're interested in the temporal dynamics of the brain. And somebody briefly alluded to the use of microstate analysis. And there's something we've done here where we've looked at how the temporal dynamics of the activation of resting state EEG change as people fall asleep. But if you don't know what microstate analysis is, it's not that complicated. Essentially what you're doing is looking at the global field power of a bunch of EEG signals and looking at peaks and troughs in terms of peaks where there are a lot of topographical differentiation in voltages and troughs where there isn't. And what turns out to be the case is that brain seems to cycle through a series of such peaks. And if you take all those peaks and do some simple unsupervised machine learning on it, you can identify basically a set of topographs that seem to recur in time. Right? They seem to recur in time. And this is not something I've come up with. It's well established and has been around for at least 2 decades as a technique. And there have been improvements using hidden Markov modeling and so on that essentially validate this idea and show that there are these topographs that seem to repeat themselves. But what I'm interested in here is not those topographs themselves, but how do they change when you fall asleep? So what we first of all see is if you look at these microstates in wakefulness, and look at the amount of power in different microstates, well, essentially you see what you'd expect. During wakefulness, the solid lines, there's a big alpha peak in all of the microstates. There's not a lot going on anywhere else. There's certainly not any difference between the different microstates. So the spectral content of the microstates of these little periods of time that only last for a few hundred milliseconds is roughly the same. And when people fall asleep, the dashed lines, the alpha peak disappears, and there's a relative increase in the theta range. Okay, so that's so far so clear and consistent, but also perhaps boring. But when you start looking at connectivity, when you start looking at the amount of just phase relationships across those frequencies in those same microstates, you see a very different pattern. The microstates don't all behave the same way. There is more variation across the microstates in terms of how much connectivity in different frequency bands that they carry. And to sort of unpack that further, what you see is that, I hope you can see the picture somewhat, but basically shows that across the 4 microstates, a particular microstate that's actually often in the previous literature already implicated in as one that increases when people fall asleep is the one that also carries a lot of theta connectivity. And what we showed was that this is not just at the group level, but that you can take this connectivity and estimate it at a single trial level, right? You can look at each of these trials where you had a bit of rest and then they pressed a button based on a stimulus or didn't press a button when they fell asleep. What you can do is try to classify based on whether in the resting period, how much of connectivity in the theta band in that particular microstate, and ask the extent to which that predicts whether they're going to make a response or not immediately following. You can do a pretty good job of predicting, these are the AUCs, so response prediction AUCs, and showing that in particular microstate D contributes to a lot of the predictive power. So the extent to which the brain in the preceding period, a few seconds before the stimulus comes along, the extent to which the brain is in that state predicts whether or not you're going to make a response when the stimulus does come along. That's interesting. That suggests that these resting brain dynamics have a contribution. They change the extent to which there is the ability to make a response even when people are falling asleep. Because sometimes you make a response, sometimes you don't. We just had this brief chat yesterday where Bobby mentioned, you have these periods where you sort of come up for air, you suddenly become more conscious and you make a response. What's going on? What's the difference between when the same stimulus comes along when you don't make a response as you become drowsy? We all experience this when you fall asleep tonight. It's kind of a noisy process. What's the difference between when you make a response and you don't? This suggests that there is something going on in the pattern of information, the pattern of connectivity in the brain that can help us predict that. So that's one example of where connectivity of this kind at the scalp level could be interesting in sleep. We've also tried to validate it with general anesthesia. So other people have tried to do the same thing. Now again, I'm using the TMS idea as a thread all through my presentation. This is a paper where they did the TMS thing, but they then gave people propofol, which we'll hear a lot about, I'm sure, later today. But essentially, it's a very common general anesthetic. It basically puts you into a deep, dreamless sleep. It's used for surgery all over the world every day, 60,000 times a day in the US or something like that. So it's extremely popular anesthetic. And if you then do the TMS thing I just told you about in people who have now are completely under, same story, you have very little complexity in the signal. The peak of the signal hardly moves from where the stimulation point was. So showing that, again, same point, if you take away consciousness from a brain, you remove the complexity of the response, which Tononi would interpret as removing integration and also removing differentiation, because irrespective of where you pulse, you pretty much get the same stereotypical response. So again, that's evidence, certainly from Tononi's perspective, about the fact that IIT has something to say about the nature of consciousness and its loss in this context. So we tried something similar. We basically took people through a sequence of anesthetic states, starting from mild to moderate to back, and measured in their brains the extent to which there is such connectivity. Again, like I said, this is a completely different group of participants. We can measure the same frontoparietal pattern of connectivity, which basically says, okay, there are these senses that seem to have more of a phase relationship with others that tend to be across frontoparietal areas. I'm not making any claims about where that is coming from. I simply don't know. However, what is clear is that when you become unconscious, that pattern definitely shifts to a very typical pattern that is seen in anesthesia. If you know anything about propofol, you will know about what they call alpha anteriorization in the propofol literature, which is basically saying that in the alpha band, you get this particular frontal peak. And in the clinical context, that's often used as a way to indicate to the anesthesiologist that this patient is under. And if you know about BIS monitoring and so on, it's basically trying to pick up on that to some extent by indicating that, well, if that is there, that frontal activity is there, and in this case, connectivity, that indicates this person's under. And exactly what we see in our context, and that the same brain will eventually recover that original pattern of connectivity as they come back up after the drug's worn off. Again, this is just validation of the bigger picture. This is basically showing that what I expect to see in terms of what I know about anesthesia or what I know about sleep is indeed manifested at the scalp level, though we don't know where it's coming from necessarily. What we also show, and this is interesting, I didn't expect to find this, but I did, was that if you look at our participant group who went through this anesthetic initiation, there were some, because we didn't give them as much anesthetic as you would get in a clinical setting. We gave them much less. The reason that was interesting was because then you could see, well, some people remained conscious under the influence of the drug. So this is looking at, we gave them a task to do, I should say, and they kept doing the task as they fell asleep. Sorry, as they went under with the drug. But some of them did go under, others didn't. So that's the red versus the cyan. And the reason these guys didn't go under because they didn't get enough drug, but that's interesting. But the point is to compare them to people who did go under. What turned out to be the case is that the presence of increased alpha power and connectivity in the baseline before they got the drug predicted who would go under and who would not. And that's interesting, suggesting that what's happening here, this is just the average across everybody, but if you look at the variation across people, you get an indication of who's going to go under and who's not. And it's important to say that at baseline, all of them did a perceptual task, very simple task. They all aced it. They all got 100% or close to 100% accuracy. So just based on behavior, you couldn't say this person is not going to go under, whereas this person is. But if you look at the EEG, you can say a lot more. And that's really interesting because, of course, that has implications in the clinical context if we can find a way to do that robustly in a real-world setting, right? So that's something that we showed in this paper. That connectivity, as I said, predicts the loss of consciousness, at least in the context of sedation. It shows interesting information that you can't see otherwise. So what I'll now do is, I've talked all this time about states of consciousness. I've hopefully shown you that, okay, we can measure something about states of consciousness using these sorts of techniques. But I'll also hopefully tell you, try to convince you about the fact that you can also measure something about contents in the time that I have. Now, what do I mean by contents? So here's one way to measure contents, and that's to basically compare different contents of consciousness using a bistable perception task, where The stimuli, in this case, are sounds like this. So you hear like a horse galloping, or the two streams separate out because they're coming from one ear or the other. So the top set of stimuli coming to one ear and the bottom to the other. And usually you'd perceive a stream of galloping sounds, but sometimes just spontaneously that stream will switch to two separate sounds in two separate ears. That's what you'll perceive. So there's a spontaneous change in the state of perception. You might know of binocular rivalry in the visual context. This is essentially an auditory equivalent of that, where people perceive either one integrated stream of galloping sounds or two separate streams of sounds which basically are separate into two ears, right? So there's left versus right. And it changes one to the other. So we ask people, press a button when you sense a change from one percept to the other. And then we can look at, in the brain, what was different before or after this self-generated, so endogenously generated change in the percept. The physical stimuli are not changing at all, I should point out. It's just the perception of the stimuli that's changing. Okay? So if you do that, and then look at, again, a measure that captures the extent to which there is connectivity in the brain, and I'm using now a different measure that is proposed, that's been proposed by the group in Paris at the ICM, which basically is eschewing the idea of phase relationships and instead looking at nonlinear relationships in the signal using a well-established technique called permutation entropy, which is on this whiteboard yesterday, actually, for some strange reason. So it's clearly people here who are working on that. So permutation entropy, it can be measured in any signal by basically taking that any signal, converting it into a series of symbols, in this case, 3 triplets that basically make up different kinds of symbols. So each shape is a particular symbol, and then calculating the extent to which there is mutual information across these symbols, right? And asking basically whether when this symbol occurs in one channel, what's the probability that this other symbol occurs in another channel? Now, unsurprisingly, this will be hugely contaminated by volume conduction, right? Because channels next to each other will behave the same way. So what they've done, this is not my work, I'm basically paraphrasing their current biology paper. They've then basically then come up with a weighting matrix that tries to essentially ameliorate, as always, the influence of volume conduction, to then try to identify or remove the influence of dipolar sources to see the extent, to kind of measure the extent to which there are multiple sources, right? And then produce a connectivity map of the same way. But this, they would call, is essentially an information theoretic measure. It's not at all related to phase relationships, right? And what we found was that this measure, which supposedly is able to capture nonlinear relationships, because there is a lot of theoretical work in the physics world, permutation entropy comes from there, showing that permutation entropy relationships between signals is essentially, can capture nonlinear relationships between those signals. For example, some other measures that, for example, phase relationships, which are ultimately linear, cannot capture. So this is a nonlinear measure. Long story short, that's their claim. So what we found was when you have endogenous bistability, so when you go from perceiving, in this case, if you look at the red line, when you're perceiving two streams, you feel that there's one series of sounds in one ear, another series of sounds in another ear, and they're two different things. And then suddenly, after a while of listening to these, your brain switches to feeling, oh, that feels like a galloping sound now. And then you look at what in the brain changed between those two situations because they pressed a button here, and then you see that the amount of information sharing as measured by this weighted symbolic mutual information measure, this one based on permutation entropy, it switches from being slightly lower to slightly higher. So basically you get a crossover effect when you go from a two-stream percept to a one-stream percept, and vice versa when you go from a one-stream to a two-stream percept. Now, this is interesting, which is the first study we've tried to do this, and this is something that we're still getting our heads around, because what we found was it seems to be fairly evident that there is an increase in the overall level of connectivity when people say they feel this versus that. Nothing's changed in the stimulus sequence. People just tell me what they feel, and then I look at what's changing in their brain. It going from before change to after change, when you go from a two-stream percept to one-stream percept, the amount of connectivity, when I say connectivity, I mean this information sharing measure increases, whereas it goes the other way, when it goes from a one-stream percept to a two-stream percept. What's more, if you just look at connectivity, the spectral sense, so using phase relationships, you get nothing. There's no evidence of any such crossover effect. And when we ask people to basically, we change the stimulus, we change the experiment where we now introduce a induce, we change the stimulus a bit to then induce either a one stream or a two stream percept by changing the gap between the sounds. So this is an exogenous condition where the previous time nothing was changing in the stimuli, they were just changing what they felt. Here, we change the stimuli a bit. Now, again, that effect in that information sharing measure disappears, right? Which is interesting. So basically, when it is an endogenously generated percept, it seems to be captured by this relationship. Now, whether that's something we can reproduce was a big, big question for us. We said, well, how do we know? We can do source reconstruction, but we can also, in this case, have access to some intracranial data. So this is an intracranial patient from Argentina who had, by sheer luck, two surface electrodes in middle frontal gyrus and superior parietal lobe. And we showed that the same pattern exists. So when they have an endogenous bistable perception switch, they produce the same measure, same technique. Nothing is changed except that it's an intracranial signal. And you see this switch over, which then disappears if it's an exogenous condition in the same patient. Right? So that's interesting. And also the fact that basically you can't see anything in the spectral connectivity. And I should also say on top of all this, when we looked at the same ideas but across temporal senses, nothing again. So between frontal and parietal senses, either on the scalp or inside the brain, or on the surface of the brain, I should say, is where we found the presence of information sharing, if you want to call it that. Certainly Tononi would call it that, between signals that indexes the extent to which a certain percept exists in the brain. So it's important to clarify that this is, in a sense, contents, because the state of this person is unchanged as far as experimental manipulation goes, but the contents of their consciousness, what are you feeling right now, what are you perceiving right now, has changed across these two conditions, and we're measuring that using EEG. Now, this is just a starting point, however. There's lots of questions that still remain unanswered, but what I'm hoping is that with these sorts of tools, as they become more sophisticated, things like RSA, so representational similarity analysis that Nico Kriegeskorte developed for fMRI, can also then find application here to be able to tease apart at the source level the set of representations so the set of signals in the brain that captures a particular representation that you hold in mind at any given time, especially endogenous ones. Those are particularly hard to catch because they're not stimulus driven. They just like in the resting brain, they change at will. We don't really control them. So that's kind of where I'll leave that bit to rest and hope to come back to it in the discussion. I'll finish off in the time that I have with coming back to something clinical, because as I said, as of my title, a lot of my work is indeed driven toward, well, how can we use some of this to make a difference in the clinical context? And this is where my work with Adrian really intersected, because I started looking at this with EEG, looking at these patients, and I'm not the only one. Again, coming back to TMS, keep recurring with that theme, as you can see. The same group in Italy has done that too. They've used TMS with EEG. They've zapped these people's brains, patients in vegetative, minimally conscious states, and they zip it. What do I mean by that? So they call this technique Zap and Zip. It's very, very catchy. So what they do is they zap their brains, and they literally zip the signals generated using like a zip file that you would zip on your computer. Why is that a good idea? It's because the algorithm, the Lempel-Ziv algorithm that is used for zipping most commonly, is essentially capturing the zippability of a file is the extent to which that file has redundant information in it. Same idea here. If the signal is complex, you can't zip it much. So if you can calculate a number, the extent to which the file size has changed as a result of that zipping, you can calculate the extent to which this brain has or has not got complexity in terms of the time series we can measure. That's essentially this measure they call PCI, Perturbational Complexity Index. It's a linear, it's a scalar number that collapses the complexity of consciousness down along one dimension. But when done, it basically pretty much produces very, very nice, well, I'd say in this context, in patient data, it's hard to find a linear trend like that, where as you go from vegetative to minimally conscious to emergent to locked-in patients to healthy controls, you basically produce a progressive increase in the amount of zippability, a progressive decrease in the amount of zippability of this file, right? So vegetative patients have a signal that can really be zipped up and has not much complexity. So they showed that there's a clear linear trend that's very significant, and you can see individual patients here. That's a locked-in patient who is, for all intents and purposes, fully conscious, produces a lot of complexity compared to a minimally conscious, compared to a vegetative patient where there's really a massive loss of signal diversity across the cortical surface. This is interesting and certainly got a lot of attention. We've tried to do that in the resting state. Again, the same techniques haven't really changed anything in what I'm doing, But this is data from Stephen Laurie's group in Liège, 104 patients across these different states who basically, they use 256 channel EEG. 10 minutes of data acquired in the resting state. Patients are not doing anything. We're not asking them to do anything. I'm just measuring the extent to which we can capture connectivity. And again, in many of these cases, the challenge always is either the patients have so much cortical damage that either they can't go in the MRI, so not all of them have MRI, even if they do, the MRI is unusable. So there's all these real world challenges. But from a clinical perspective, you can't pick and choose. I would not want to pick and choose which patients I can say something about. What can I say about how much information there is in any given brain? That's really what we started off with. But what we essentially showed in this paper was that there is a fairly good linear progression in the extent to which there is connectivity measured exactly like I showed you before in these patients. And if I use a simple measure, a measure that has been popularized by Olaf Spons and his group in Indiana, basically capturing the extent, in MRI anyways, capturing the extent to which in resting state MRI or in fact, DTI imaging, there are hubs, regions of the brain that connect either physically or in functionally in MRI, other regions of the brain to each other. Same thing if you measure that in these networks, you basically can capture that by the presence of the nodes like that, nodes that you can't quite see the coloring in here, but there are two. You can say, well, there's this network, this little toy network has two modules in it, one over there, one over here, and that those modules are interconnected by specific nodes that sort of bridge across these modules. So the extent to which there are such nodes in any given network can be captured by a number. And if you do that, you get a fairly nice linear trend in basically the relationship between the behavioral measurement made with a behavioral scale. I should say that these measurements are made using what is called the coma recovery scale, which is something that we take for granted, but it's a measure that captures the extent to which there is behavioral information about consciousness in the patient's clinical profile. So a well-trained clinical neurologist will basically be able to administer the scale and produce an assessment of whether the patient is totally vegetative or, as Stephen Laurie's group like to call it, unresponsive, or locked in or somewhere along that spectrum. And what we find is that, if you can look at the presence of such connectivity, you can basically produce a linear trend. There's a lot of spread, unsurprisingly. I'm not saying that it's all very, very easy, but there is a clear linear trend that is statistically significant across groups. And what's more, what we also did was compare multiple measures you can extract from the EEG. As we already discussed, the EEG is a much richer signal than sometimes it's easy to deal with. It's certainly a three-dimensional tensor. We have at least two dimensions here. The third dimension of time is the one that we collapse to calculate this connectivity. And then you can ask, how do power versus connectivity versus these graph theoretic measures explain what you can see? This is rank ordering, essentially showing you that in some cases, in some discriminations between patient groups, some connectivity measures, for example, alpha band activity is very useful, whereas to differentiate other groups, power in the delta band is very useful. These are just measures ranked by the AUC. And if you then put these measures together in a simple classifier, just an SVM, you can basically produce a fairly good classification of the extent to which this patient can be classed into one of behavioral categories. And what's more, this is something Adrian alluded to, the fact that sometimes the EEG produces misclassification. So for example here, where the EEG says the patient is minimally conscious, but the clinicians agree that this patient is completely unresponsive. In those cases versus cases in which the EEG and the behavioral diagnosis completely agree, if you look at the proportions of patients who then go on to make a recovery a year later, in patients in whom the EEG found something, have a much better chance of recovery in the data that we had. And that's promising, hopefully suggesting that the EEG, analyzed in whatever way that's most optimal, can provide clinically relevant information, and that's important. But it's not just that. We can also compare the EEG to something that we know as ground truth after Adrian's work across multiple papers. So you know this figure. I'm not going to say anything more about it. It's world famous. And essentially says there are patients who can play tennis. OK. The question then is, what do their connectivity patterns look like? Here's yours. This is one adult in whom I've measured EEG for 10 minutes. A typical vegetative patient might look like that, a dramatic loss in the amount of connectivity you can measure. But there are also patients like this one. These are all both patients I tested myself at Cambridge. Both of them had a behavioral diagnosis of vegetatives. There's nothing going on as far as the clinician is concerned, at the bedside in either of these patients. But this patient, while was unable to play any tennis based on Clayton's task, but this patient was tennis positive. So there is some correspondence across these modalities that is promising. We've also ensured that we can compare this with something like PET. So PET, of course, is a measure that you're all aware of. It measures metabolism in the brain. Unsurprisingly, if you compare patients who've got a positive PET response, what do I mean by that? PET responses indicate that there is at least partially preserved metabolism in frontoparietal cortex. That's a PET positive patient versus a PET minus or PET negative patient who's got complete hypometabolism across cortex. If you compare such patients and look at their connectivity, it's bleedingly obvious, as it is for a classifier that can then predict and generalize the PET diagnosis. And it's important to say that this classifier was given the vegetative, the minimally conscious minus, the minimally conscious plus patients to train itself on, and it predicted that all LIST patients, EMCS patients, and controls are PET positive. So that's just a simple first-level generalization. Can this classifier, given new data, identify the PET diagnosis? And as you would expect, of course, all these groups of people, certainly the controls, should be PET positive, as the classifier indicated. And just to sort of show you a real example, these are individual patients now compared to controls, their PET activations, and their EEG. So the more metabolism you see in the PET, you tend to see a fairly good correlation with the EEG. I should say this isn't all by chance. We try to make sure that we can, the big problem with these patients is variation through the day and within hours. So we try and do the PET and EEG as close as possible in time together so that we can kind of have a correspondence we can check for. What's more, we can also use the EEG to look at outcomes. So here, we're looking at what happened to these patients a year later and comparing in this group of 104 patients in whom we were able to measure outcomes. I define outcome negative versus positive as people who basically progressed from a low responsive state to a higher responsive state, an outcome negative in which there was no such change. But what turns out is connectivity in the delta band, so increased delta power, increased low frequency activity is a very good prognosis of poor outcome. So the EEG is useful in the complementary sense too, in the sense that high activity can actually be useful to indicate, well, there is less of a likelihood of this patient getting better. Right? Again, you can build a classifier to significantly predict that outcome, not as well as you can for other things, but still significant. And finally, coming to the last part of my talk, what I wanted to show you that this can actually be useful in the clinical context for clinicians amongst you. Here's a situation that clinicians have to face every day. If you take our group of patients and then look at what the clinician referring this patient to our specialist assessment said about the patient's behavioral state. So sometimes clinicians say, hey, I've got a patient for you. You know, they look unresponsive to me. They look vegetative. Or they'll say, well, this patient actually has something going on. Right? So they'll say, they usually say either they're unresponsive or they have minimal consciousness. That's the level of expertise a sort of a typical GP or a clinician might be able to give without expert assessment. So if you look at that diagnosis the clinician gave us and the diagnosis you can produce with a behavioral assessment like the Como recovery scale, which is much more systematic, patients fall into three groups. There are ones in whom clinicians and the Como recovery scale diagnosis agreed that this patient is fully unresponsive. So what Adrian pointed out, like Brian Young saying, this patient is definitely unresponsive. That's your blue category. Then you've got patients who are, both from the clinician's perspective and an expert assessment perspective, minimally conscious, so there's confluence there. But there's a significant chunk of patients who the clinician referring says there's nothing going on, but then a simple behavioral assessment says there's actually something going on here. This patient has some minimal consciousness, and that's a big deal. I should point out, Adrian's patients, the ones who can do tennis, actually are, in fact, a subset of that 17, in whom the behavioral diagnosis from the clinicians and the Como recovery scale says there's nothing going on, and they put them in the scanner, they play tennis. So that's on top of all this. So there's so much room for misdiagnosis in this context. And then if you look at, again, the connectivity, that giveaway, these are patients in whom there was an accurate diagnosis, both from the clinician, as in there was agreement between the clinician's diagnosis and this Como recovery scale. These are patients in whom both the clinician and the Como recovery scale said there is something going on. But these are patients in whom the clinician referring, this is where the patient lives. This is the clinician who is in charge of taking care of that patient for decades. They think this patient is unresponsive, right? But an expert assessment, if you're lucky to get one as a patient, suggests that there is something going on. And if you look at the EEG, statistically indistinguishable from the patients who are actually diagnosed as minimally conscious. And we checked that the classifier we had built earlier diagnosed all of these patients as minimally conscious, while the clinician, as I said, considered them unresponsive. Not that the clinician is wrong, it's just that the evidence in behavior is limited. So there is convergence in individual patients, and that gives us hope. In that one patient I showed you, who had that remarkably robust pattern of connectivity, alpha power going on and so on, but was behaviorally unresponsive, produces the P300B for a task that we gave them, and of course played tennis according to Adrian's task. All of this convergent evidence in that one vegetative patient, and here is his discharge report from Addenbrooke's. He left in 2011, and I just take a snippet from his report. It says he was in a coma throughout his stay, during the time that we measured all this, and that at the time he was discharged, after he left, after we'd done all this, he was still classed as being in coma. So the clinicians we work with have a challenge like that to deal with, because there is such discordance. And this patient then went on to make a recovery a year later, a recovery that meant that he could go home. And that is very rare, of course, but it's a young man with a traumatic injury that knocks out enough of the brain that is impossible to measure behavior. It can happen. So what we're trying to do now is take this forward to try and assess patients at the bedside. Adrian's already, of course, pioneering this in Canada. He's got his EEG Jeep and potentially even more in terms of hardware, but that basically allows him to go and test at the bedside, which is what we're trying to do at a smaller scale on a small island. And what we find is stuff like this. So here are basically the same. This is basically data from one patient assessed repeatedly every 3 months, systematically, 6 times over a period of 2 years. Patients make a complex pattern of recovery. Some recover, some don't, some go down, some go up. We don't control any of that. There's lots of complexity in what happens to these patients in terms of their care. But what we're trying to see is, can we measure anything useful? The colors are not, they're kind of washed out, but essentially, hopefully you can see that as the behavioral diagnosis changes, as the extent of behavior that can be measured along the y-axis here, using that coma recovery scale again, changes, so does the EEG pattern of connectivity. And this applies to power. Different sets of measures in the EEG pretty much show the same pattern, that there is something in the EEG that is useful, and is not just in individual patients measured once, but the same patient measured longitudinally over time. So it's like a prospective study of a particular way of assessing patients at the bedside using their brain activity, which is currently unavailable unless you happen to be in one of these studies in a select few places. And that's kind of where we have to change the state of play, and that's going to bring me to the end of my talk. And this is potentially a forum where we can do that in a way that's robust and identify the best set of tools that will help us deal with the challenges. Because I don't think, as we've discussed yesterday, there isn't one way to do all of this correctly. There are different source reconstruction techniques that can work in some of these patients. What if you don't have MRI? What can you say? But we need some sort of protocolization. Otherwise, it's too open-ended for any clinician in any hospital to say, well, here's a thing we could get for our patient here. That's what we need to provide. If a clinician calls me up from Newcastle, I need to be able to say, here's what we can do for you, rather than, well, we've got all these problems and we're still working on it. That's what we've been saying, but how can we move beyond that? So hopefully, I've tried to show you that you can use connectivity of this form in sleep and sedation to validate, and then in the case of patients to use as a means to assess. I'm completely aware, of course, and this is like something I point out to everybody. These are patients. We show these things to family members and clinicians, but tell them that we don't know where this is coming from. EEG is not the tool that can tell you that, not in this formulation anyway. But it is a shadow of something that could be useful. There are lots of challenges. However, the applications make it very important that we try and solve these challenges. If we can make this reliable at the bedside, then of course it's a very good complement. EEG can be a valuable screening tool, valuable triage mechanism for exactly what Adrian pointed out, where you can't possibly get every patient in the scanner and ask them to spell letters and figure out 80% of them can't and 20% can. To find that 20%, we need a way to be able to have a wide sort of opening in that filter mechanism, and this could be one way into that, hopefully. I've convinced you of that. So with that, I should really stop by thanking. This is going to be an incomplete list, but all the different people who've been involved in lots of the different studies. In particular, Corinne, who spent a heck of a lot of time traveling around Cambridgeshire in her car with the EEG in the boot and collected more than 160 such assessments. And working with these patients is hard at the best of times, so she's done a very good job, so I should thank her in particular. And of course, all the funders. And you, thanks for your attention.
force.
Tour de force.
Thank you, Shrivas. I'm sure there are questions for Shrivas. We have about 10 minutes.
Hi, that was great stuff. I just had a couple of questions about the maybe seeking some more explanation on the connectivity versus power stuff. So when you were talking about slipping into different states of sleep,
Yes.
you know, there's known things, as you said, about alpha power and theta power
Absolutely.
changes, and they seem to be mirrored in the connectivity things. So I'm just wondering how much the connectivity measures and power measures dissociate. I know you referred to another table.
Yeah. So generally you can't see much connectivity if you don't have power. But in that microstate figure I showed you, can bring it up if you like. Power doesn't dissociate across microstates, but connectivity did. Right? Now, I'd like to find out how that's looking inside the brain, because that's really the question I want to be able to answer. But the short answer to your question is yes, there are specific things that connectivity brings out that power doesn't, and that is exactly of interest. Why does it do that? And what does that mean for being able to measure the circuitry that is changing as a function of falling asleep?
Just related to that then, I wonder sometimes about how best to combine those two pieces of information, power and connectivity. In
Right.
some respects, they're maybe adding complementary information, but in one other respect, I sometimes get worried about connectivity that, as you say, when power is low, connectivity is going to be low. When
Right,
power
yeah,
is
so they're
high,
only
you have a better chance of
quasi-orthogonal
it.
at best.
So I sometimes
yeah.
wonder, should people be normalizing their connectivity measures by
By
the
power,
power?
yeah.
I don't know.
And that's something I do in what I've shown you. And not only that, I normalize the graph theory relative to the connectivity. So it's 3 levels, right? So you've got power, connectivity, and network analysis. Each measure is normalized against differences in the previous level, so that then you can't make, so you're trying to avoid any redundant claims of that. But absolutely, that's a very valid point. One needs to correct for. So this is the thing. It's full of caveats. I mean, that's a whole lecture of all the caveats. But as at MNI, we should be able to bring the minds together to be able to work out a protocolization of those caveats, like they've done if you think about in machine learning, and all that, to try and find a way to formalize some of those things. Absolutely.
Yeah, thank you. That was terrific. I have a question. I'm not entirely sure about the added value of the stimulation protocol. You presented sort of on the one hand these global connectivity measures
Right.
as indices of what's going on,
Right.
but also perturbation of those.
The conscious content example.
Yeah.
Yeah.
So I guess I have 2 questions. One is, what is the added value of doing the
Right.
stimulation? And secondly, if you use TMS, of course, that's very direct stimulus, but it's also invasive. So could you do stimulation with rhythmic auditory input, for instance, instead of TMS
Right.
to achieve the same effect?
So the first question was in the context of that bistable perception stimulus, where the horse versus Morse, as we call it, that was just a way in healthy controls. That has not been done in patients. Just as an interest from the cognitive neuroscience perspective, can we measure anything in the brain that is different between 2 percepts that you have of the same physical stimulus? That was just the aim, just to study that. In the TMS stimulation context, yes, TMS is like a blunt, very powerful, very invasive tool, but it works very well because it's such a powerful signal you're getting out of that impulse is sending in. Now, there has been work to try and replace that with auditory stimulation. As you can imagine, the response you're going to get, the stimulus change you're going to get is much weaker, but it's open to debate whether we can reach the same level of capability as TMS can. I think we could be able to, but we'd have to find the right kind of stimuli. With TMS, you've got something that really works across all these populations. You can pretty much just throw anything at it, you'll see the response. With auditory stimulation, you'd have to find something that produces a robust, reliable response, and then, of course, validate it with sedation to see how it changes. And so we've tried using steady-state stimulation, for example, and that does work quite well, but it comes with its own caveats. But we can have that discussion separately. But auditory steady-state stimulation is one way, and that usually produces quite a robust response in patients, independent of their ability to comply with the stimulus. So that's other task. There is no task. We just stimulate them with a 40 hertz or a lower or a 40 and 80 hertz amplitude modulated sine wave, and that does work quite well.
Sure, but that's the sort of induced response.
Right.
But I'm thinking about the idea of the ringing that occurs after you.
Right. So
finish.
yeah, so I'd love to talk about the right kind of stimuli to do that. I'm not an expert in auditory neuroscience, so yeah, I should say My experience there is limited, but that's something it would be great to discuss, what kind of stimuli could produce such a reverberation that you can measure the complexity of. Absolutely. So Anil Seth, who I'm sure many of you know of, has produced papers showing that in resting state data, they are measuring an equivalent of that response. They're basically is resting state data, but they're capturing the signal complexity using the same sort of information theoretic measure, the idea of zipping. And they show that at resting state, they can actually do a pretty good job of differentiating states, but that's in sedation. They've not done that in patients yet. So I can point you to that paper, I think it's in PLOS One. But again, so the measures are capable of capturing signal dynamics, but ultimately to make a clinical tool, you want, it's not just about p-values, it's about effect size. That's why TMS is great. So replacement for that, which can produce the same effect sizes that TMS does, that would be great. That would be great.
I was thinking about it. I'd like to get your thoughts on the reasons or the explanations for the lack of integrations after stimulation in TMS.
Right.
In fact, there is reduction. What do you think is the functional role of this?
So you're stimulating with TMS and you don't get integration in sleep, or are you?
With sleep, yeah. In
Right.
particular,
So
yeah.
why does that happen? That's a good question. To be honest with you, I don't think that people who've done that technique really understand, except to say that, well, from a neurophysiological perspective, what sleep causes is a functional change that changes the extent to which different brain areas tend to be doing different things. So slow wave sleep generally is characterized by, you know this a lot better than I do, large scale, very powerful oscillations that are similar across cortex, which in the TMS response is reflected as essentially not all brain regions doing nothing, but doing the same thing. And that leads to a lower perturbational complexity. So sleep, the TMS response is kind of collapsing lots of different things into one thing, which is in patients, you might see nothing or very little. In sleep, you might see a lot, but not a lot of variation across brain areas. That's how they would capture it. But what in sleep is doing that? I don't think TMS can tell you that. It simply cannot, because the resting state measure, it's very crude and very simplistic. For that, you need tasks, you need the kind of stuff that sleep neuroscientists do with great detail to understand that the response. But TMS could be a tool, for example, with a task during sleep. Then you're in more interesting territory, I think, to answer the question you're asking.
EEG.
Lower.
How well they adapt to lower density?
So in the paper, it's a supplementary figure where we decimate electrodes. Long story short, as Pedro mentioned yesterday, you still preserve a lot of the information you need. You can't produce detailed images, but the core idea of the core pattern I've shown persists. I think down to 16 electrodes. Not that many anymore. But the patterns are still significant. But you can't really visualize those maps in an interesting way. But you can take the average and still say something. Absolutely. Yes, right. I'm throwing away all the dynamics in the system. I didn't go into it, but we've done a dynamical version of that where you can look at the variation, but essentially that's moving from collapsing across time to looking at the variation across time. One could do that. You get interesting patterns, but interpreting those patterns in each patient may or may not make much sense because you need a handle on what that variability represents. So in the movie context, if you think about it there, you have a handle on what the person is going through, and then you could look at the variability of, let's say, a particular measure in the brain to see is there evidence of integration of the visuals, the sound, and all the other percepts that go along with, all the other features that go along with watching a movie. So that would be a context where that would be a very good application. But here, we were just trying to do the most simple thing, throw away variability. If I can see anything that is stable in this patient in 10 minutes, it's very noddy.
Excellent. Well, we are right on 11 o'clock, so thanks again, Srivas.
Thank you.